Okay. All right. Well, it's good evening. Great pleasure to be back here once again. I'll try and make it more or sooner next time. At least something has happened in the meantime that I can show you, Will. But yeah, as Will stated, actually Will and Pete Silver and myself and Johnny Botsford, who's speaking, actually Johnny Botsford was a classmate of mine, who's speaking later this term, I guess. We were all part of a cohort of a unit that was run by, at the AA, that was run by a man called John Fraser. And John Fraser, in a way, was one of the godfathers of computation and design. And by computation and design, I'll show you some examples of what I mean. Wasn't so much about using Maya or using shape making and robotics and the sort of the fabrication sense. It was much more about understanding logic, in the sense of training your mind to think in a particularly structured way. That's what I find one of the things that has benefited me in my work since I studied with him, that it helped me to think in a more logical way, in what was at the time a very illogical school. So that is something I think that has a lot of value. When you look at the computer, I look at that with my kids right now, my children, that the computer's ready and easy to use nowadays, but you actually have to look beyond the interface and think, how are things actually working, and how can I control that, or how can I better understand it to make it work for me? And as you will hopefully see, some of that has been able to translate into practice in different ways. Not what just I show you tonight. For example, Johnny went off in a different direction, equally beautiful and interesting. So one of the things that I have to say that came out of that also was cementing, if you like, a personal interest I had in the subject matter of computation. After I left the AA with my part 2, with my degree, my diploma, I went to, bless you, I went to down the road to Imperial College and got myself as a master's degree in computer science. And I think I was the only one, the only architect in a master's class full of engineers and mathematicians and physicists. And I can tell you it was very difficult because the course wasn't so much about teaching you how to write computer programs. It was about applied deductive logic, which is basically what lawyers use to read contracts. So after that, I could read contracts in our office really easily, because if this, then do that, and the clause says this, and if not, do that. And yeah, and it was also very much, I think, about the difference that you have in this country between education and training. You sort of go to university to be educated, and then you get trained on the job, So we're not going to teach you how to draw details or whatever, you're going to teach you how to think. And that was what that course was very much about. So then with all that thinking, you go out and think what I'm going to do with that, having studied with John and having done that. So this is a little bit of the fast forward of that. I've been working I used to work actually when I was a master's student at the AA back in the late 90s. I was working part-time at Zaha's office to help support my life. And then after that I went and I worked, actually I tried to be an academic, but it didn't quite work. I did that in Hong Kong for a few years, and then I worked for almost 8 years. I worked for Frank Gehry in LA, and there it was a great experience because you really learn how to build. It was a great office to learn how to build very complex things using some very, very advanced technology. If you look at the history of Gehry, the use of CATIA, the use of other software that is really very much about fabricating and making things. So then, I came back to London and spent, a little bit over a decade now at Zaha's, where as one of the things that I have been focusing on, besides building quite a few jobs, has been building up a new line of business in the firm, which is the aviation business. You may have read over the past week that a new airport was opened in Beijing, and that was my project. So we finished that, and we're now working on some new stuff in India and elsewhere. And so it's building a business and looking how can you use particular knowledge that you have to do that is something I hope I'll show you tonight. So without further ado, so we'll talk a little bit about sort of tech transfer. We'll talk a little bit about rule-based design, because that's what Will had originally put on the title of the lecture. We'll talk about how you design a bit of airports, and then we'll talk a little bit about Beijing Daxing Airport itself. I like to show these slides simply because it's a little bit of allowing you to take a step back. And one of the things I found most fascinating in my career has been the idea of technology transfer and learning from, as an architect, from other fields of work. So the interesting thing about this image, this is, if you haven't been there, you have the chance to go, you should go. This is the very, very first 747 jumbo jet being built at Everett. And as you may recall, the 747 had to have a completely new factory because it was the biggest plane in the world at the time, and they built the biggest building. What's interesting about that, you see the noses of the next one, this is the first one. Back here, they're still constructing the building while they're building the first plane because they had to deliver it to Pan Am to get money to finish the building. It was that cash-strapped for a company like Boeing to do that. So they rolled out the plane, they're still building the highway, they're still building the runway, and the office building is a tent. So literally it ends here, like you still have to then take it there and get it off the ground. The very first plane was what they called the plane that nearly ate Seattle, because had this not worked out, that would have been the end of it. Because of that, all the technological innovation that happened, fast forwarding now many years, was how do you control a complex project like that? And one of the things that Boeing developed working with CATIA, and this is obviously a lot of the work that came out of technology, interdisciplinary research that we established back when I was at Gary's office, was the idea that not only could you document in this case, the aircraft completely digitally, but you didn't even produce any drawings anymore. So the aircraft here that you see in the model is what you call a virtual mock-up. Each one of these pieces actually is a true solid with physics properties. It really behaves like aluminum or titanium or whatever the different wing spars are. Out of that you can calculate weight, you can calculate the performance of the plane, and you will know exactly how this thing will perform before you even cut the first metal. And to perform that cutting of metal, you need what you call, they literally invented in your work, the idea of authoritative data, which means this data is released, much like when you can release a construction document, but is released directly to CNC machines to begin cutting metal and putting this plane together. So if you go beyond that, which was like the 777 notion, and you go to the Dreamliner, you can fly these things from Heathrow nowadays. I went to Everett and I had the pleasure of actually seeing the very first one being put together. Not only did you digitize the documentation, the control of the information into a digital model, but you actually decentralized in a digital fashion the complete production of it. So you can see different pieces are designed and made in different parts of the world and then brought together to Everett to be assembled. And what's interesting here is that not only would you go offline to manufacture them elsewhere, but they would actually outsource the design. So the interesting thing that's interesting about the Dreamliner, the 787 that you can fly, is when they started working on this at Boeing, the Soviet Union had collapsed not long ago, as you know, in the 1990s. And they started looking over the 90s how to design this new aircraft. And so what Boeing did is they found that in Russia, the ex-Soviet Union, Moscow, they had a lot of very capable but unemployed aviation engineers who were very, very smart, but they said, you know, for a fraction of the cost, they set up a design studio in Moscow where all these design engineers working with a Boeing name tag designed the Dreamliner. So what most people don't know is that the 787 Dreamliner is actually a Russian plane, right? Something worth thinking about. So there they are being put together. And so what happens after that is you not only simulate the performance of the aircraft, but you actually simulate the production as well. So in this case, this factory in Everett, where you're putting together pre-assembled pieces, you know the entire plane is made of plastic, it's made of carbon fiber. I think metal on the plane is now something like less than 7%, something like that. This componentization and kit of parts is something that tells you, okay, what has happened over the lifetime of these aircraft that I showed you, the jumbo jet, the 777 and the Dreamliner. And one thing that you found, or that we found, that I've been kind of reading up on, is that you went from a huge number of individual parts. You know, the Boeing 747 used to be 3 million parts flying in close formation. They just happened to be attached together. With a huge amount of centralized design, paper drawing, centralized production, everything design and production happening in one factory with one source of knowledge, one location where everything sits, to still having a centralized design, but now a decentralized form of manufacturing around the world, and reducing the number of individual parts by having larger integrated components, to then going all the way to the Dreamliner where you actually decentralizing the design itself. Design is now distributed around the world. And you go down to still many, but only 100,000 parts. So what you're having is that the number of parts is decreasing, the proprietary knowledge of one firm is decreasing because it's shared. But of course, when you do like that, you decrease the risk because now many companies are supporting what is a complex, expensive project. But the amount of management that happens goes up exponentially, right? So it's a different way of working. So if you take that into architecture and you start thinking, well, curvy buildings, you know, Gehry, Zaha, a lot of people doing curvy buildings. Well, guess what? Eero Saarinen did that way back in the 60s. If you think of the TWA terminal, which is now, by the way, a very cool hotel. So if you go to New York, you can stay in the TWA hotel. We're using very simple, basic, paper-based, handcrafted construction that came from, like, say, lofting wings of a Spitfire, right? That then went into, if you go forward to, say, Gehry's days, where again, you centralized the design, you still had kind of an assembly of digital craftsmanship to produce these buildings with a kind of a form of mocking up, and then putting things together through traditional shop drawings. This is a project that I was responsible in Beijing a few years ago, the Galaxy Soho. That went further and actually look at decentralizing the design through parametric design, which is rule-based design. Now I can use that word, or mention it, in which we're looking at configurations of buildings, in this case looking at what can you design that adheres to a particular constructability framework, in this case the maturity of the Chinese construction industry. So you're going to design to a budget within that industry, what can I achieve? So it's basically a form of mass customization based on capabilities of a particular industry, minimizing the amount of import, in this case, that you have to do. So there's an analogy there again, where we're moving standardization. We don't have to design boxes anymore. We can design much more interesting things. But the amount of management that's required to put all this stuff together is now very, very large. So we're going from, and you know, my colleague who's here tonight, Clara, who's been working with me on the airport in Mumbai we're designing at the moment, knows that the level of management that we have to do of information and coordination is exponential. It really is huge. It's no longer a bunch of architects working together. It really is channeling information and checking off that everything works. So historically, where does that come from? So I mentioned before John Fraser and some of the research that we did. Some of the idea was, how can you, rather than drawing something or rather than producing a finite artifact, which I can either draw, I can make a physical model of, or I can take Maya and draw a shape and say, I like that shape. It's more like, how can I set up a series of codifications of rules that will then in turn produce a result? So here's a simple exercise. John, with whom we studied, developed various versions of what was called a constructor, which was essentially, in this case, intelligent cubes to which we assigned programming functions. And depending on how you stack the cubes, it was a form of physical programming, because you stacked the cube, machine read the cubes, and it would write computer code from it. And we attached that then to Lego robots, and we could get it to write Chinese characters, in this case, the name of the university we were doing research in. So suddenly, rather than saying, I have to spell this out, I can just stack cubes, and the cubes will tell it what to do. So now, rather than becoming the architect as the master designer directly, you can also say I can become architect as a master programmer, or applying certain rules, certain practices, certain way of doing things that I can codify and generate results. Another project, this is, again, we're talking the late 1990s here. There's a man called Mark Burry, who is the architect in charge, or now they're almost done now, but he's the architect in charge for the completion of the Sagrada Familia by Gaudí. And one of the things that was interesting about Gaudí's work, as you probably know, is that he used mathematical forms that could be created through physical annealing. So in another case, in a certain sense, by rotating two shapes in plan, you would intersect them and get these parabolas that would create these ridges on these columns. So what we did with Mark, we said, what about if Gaudí had the computer available and you could actually generate a Gaudí column where you have counter-rotating parabolas that are intersecting, and you calculate in real time the intersection of parabolas. If you modulate the amplitude and the number of facets on these parabolas, or number of parabolas intersecting, you can go from something that is essentially cylindrical to something that's quite wild. And this is a little piece of software that, again, was developed to do that. It's not a plugin, it's just a little standalone tool. And I'm not going to run it now for the sake of time, but you can tweak this and you can imagine these things. You can pull them and push them and come up with all kinds of versions of Gaudi columns just by applying Gaudi's logic to a computational framework. So again, further work. This one was looking at the idea of breeding. So one of the ideas behind this was, can you apply logic rules to the codification, in this case, very simple, the cage control points of a surface. In this case, it's a very twisty surface. And by having different generations, I can take different one of these and breed these together, much like you cross animals or cross breeds, and you get new breeds or new color of sheep or whatever. And you would actually control not how you're designing and pulling points on the shape, but you can control the parameters. Are you performing, for example, sexual reproduction, meaning you crossing two, or asexual, meaning just one? You have mutations, and number of mutations, and type of mutations, and you let the machine come up with proposals that you then select. So suddenly, instead of you drawing a shape, the machine is coming up with proposals for you based on a logic that is encoded within the software, which you can take into another piece of software. See, this is AutoCAD 2000, so it's a long time ago. But the idea really was, can I generate a surface or a family of surfaces purely by breeding different versions of it? So mother and father come together, produce a new generation of surfaces that have particular qualities that I might need. Now, you might attach these to something performative, which is what I'm going to show you in the aviation side. This was later on, research at Gary's. This one was about looking at towers. At the time, we were building a tower in New York. And one of the ideas was, how do you optimize with the property developer a tower to generate and maximize revenue under market uncertainty? And by market uncertainty, I mean two things. One is the type of market you want to build for. Is this all going to be residential? Is it going to be office? Is it going to be a bit of hotel and a bit of office? You know, like the Setia problem. How do I want to mix it? And the other one is the uncertainty of the construction market, meaning how can I, if I'm designing now and I'm going to go on site in a year or two's time, what's it going to be cheaper to build this in concrete, build this in steel, a mix of concrete and steel? Which material is going to be the more favorable? Because steel prices fluctuate on the market. So it's very difficult to guess, even with your QS, with your cost consultant, what's going to be the right way. You have to kind of decide. So what we did is we wrote a series of software tools that we're plugging into this 3D framework that would generate towers and very quickly using what you call a financial pro forma, which looks at the mathematical cost calculations and performance of the building. So it's going to cost me this much to build, and it will have this level of ROI, which is return on investment. So property developer will want to maximize their return on investment while minimizing the investment they make. What is the right mix of the building? Is it office? Is it retail? Is it a hotel? What is the best mix of that? And what is also potentially looking at what this thing could be made of? And again, running scenarios and looking at an annealing, which again you can select for the most appropriate scenario, understanding what risk envelopes are and understanding what the work parameters are. For example, we have zoning layouts in New York. We have certain limitations. What is the best way to make use of this piece of land and build the most cost-effective, biggest cost-generating building you can? So when you take that forward, then you look at constructability. And constructability, this is work at Gary, this is work at Zaha's, was very much about, again, using the technology not just to generate shapes, but generate shapes that were looking at a particular form of constructability. For example, this is looking at what are called scale translational surfaces, which guarantee that each one of these square facets is always flat, so you don't have to triangulate. It's a four-sided piece of glass. You reduce the number of mullions you need by a third. And you can generate very complex shapes. As you can see here, these are vacuum-formed rapid prototype shapes in the Gary office at the time. Or in this case, sheet metal. This is from Galaxy Soho, looking at, can I create a family of components that can be mass fabricated and yet still have enough diversity in them that I can get this kind of differentiation in shapes? All of that then needs to be documented, as I'm sure you're aware from your studies, in what's called BIM. And again, the translation of information from just geometry to BIM, and that BIM, the I in the BIM word is information, adding that information and storing that in tools like Revit or other such tools, becomes particularly significant. So you have now a complete loop of framing a design problem, designing it, looking for the constructability, and then documenting it. So if you look at how that works, for example, in some of our work at Zaha's, we look at a lot of data-driven design, for example, looking at functions, looking at capabilities, coming up with iterations, looking at optimizing structural layouts that we do with engineers, looking at, for example, different types of layouts of floors within a particular building. This is a building that's in construction right now in Guangzhou, I think. This is Infinitus. What kind of program, what kind of usage can I have? By program, I mean spatial program, usage types in the building. And again, in this case, look at, does this meet the client's needs? So that digital layer of conversation is always present, but you have to understand ultimately where it goes. So, on to the third topic, when we start talking about how you actually design an airport. An airport is interesting for me for a number of reasons. One of them is, I grew up in them, so because my parents used to travel a lot, so I was always kind of familiar with them. The other thing is that there's something kind of interesting and poetic about them because they're very emotional spaces. We have terms like meeters and greeters and weepers and wailers, which are the people who come and see you off when you're leaving. Go goodbye, and they come. If you're doing this in India, they'll come with like 20 people, and it's interesting because you have to cater to all these people, and it's a very emotional, very particular space. And also, what's interesting about them is, as you know, it very much levels the playing field. It's a very democratic space because, let's say, you really like to go to the museum and you really like to go to the stadium, and you won't go to the stadium, you won't go to the museum, but everybody will go to the airport unless you're a hermit nowadays, right? Everybody, I'm sure everybody in this room has been to an airport. So it's something to think about because it affects all of us, and in many ways, as you'll see, they also become a gateway to a city. It's a place where you go out into the world, or it's the first point of contact that you have. I recently went to Manila in the Philippines to talk to some new clients, and I'd never been there before. And the first impact you have is the Ninoy Aquino Airport. And it's a white box. It could be anywhere. And you think, okay, how do I know I'm in the Philippines? Or how do I project that I'm in a particular place without resorting to vernacular tchotchke or making it look like Disneyland? But how do I capture a spirit of a place or of a country? So we're exploring right that on projects in Poland, projects in Australia, in the aviation sector. Very interesting also because everybody here in this room, I think there's people from all over the world, right? And I think it's also something that ties us all together. So it's a very multicultural kind of type of project. I can also say from a technical point of view, it's probably the most complex project an architect can do today, is the airport, because of the level of systems, the level of regulations we have, and also we are dealing with all of this stuff, which are the aircraft, which are tied to very, very other completely unrelated codes to building design. So there's bodies like IATA and ICAO, which are the international bodies that govern aviation, have their own rules about how you park aircraft, and to that you have to lay out how far can people walk before they are exhausted, right? Or how far can I walk before I miss my flight? Or where do I put my shopping? Or where do I put my check-in? All that stuff that we're all familiar from using an airport all has to fit together. And if I say, well, I don't really like the shape of that, let's make this curly, well, then suddenly the airplanes don't fit. Or you can't fit as many as you need. Or do you fit many little planes or just a few big planes? Or a mix, This becomes a very, very difficult multivariable problem to solve, right? It's a multivariable, nonlinear problem you can solve as the airport. And that is also why nowadays there's probably maybe 10, 12 firms in the world that can really hack some of the really big airports not because they're only particularly difficult, but it's a very long learning curve and it's a huge investment for the company to decide, I want to get into that business. We decided it was something that the firm could relate to, and so we decided to go down that path, and 10 years later, we're kind of there. But it's a fascinating problem to work on, and I can say that I found an interesting problem for me to work on after everything I've done that brings it all together as well, as you will hopefully see. So one of the things you have here is the idea of optioneering. I mentioned optioneering with those surfaces. I mentioned the optioneering with the towers. The idea that you have suddenly an airport, which could just be a blue box, and you have maybe one or two or more runways, right? Heathrow is a good example. We have 2 runways and a bunch of little boxes. So you then have a taxonomy. This is effectively a taxonomy. These numbers mean capacity, so MPPAs means millions of passengers per year. So a good example is roughly per million passengers per year, you roughly need 10,000 square meters, grosso modo. So it tells you this will be 300,000 square meters, this will be 450,000 square meters. So they tend to be pretty big. Now, how can I organize this? Do I have X or Y shapes? This is the piers you park the planes. This is what you call the processor, which is where you check in or have your lounge or your shopping. Or do I have a satellite, which is like when you take the little train at Heathrow T5 and you go out to the remote satellite. There's pros and cons of doing that. Or do you have multiple piers, these sticks here being called piered, where you try and connect everything in one place? That also has some pros and cons. It has to do with walkability. You can walk around without needing to take the train. It reduces the investment of that. Less flexible for the aircraft, perhaps. But you have, like, which one do you pick? All of these will fit that capacity. So one of the things you do is you start looking at what have other people done in the past. And one is, of course, I'll just go through this fairly quickly. But you have to look at a couple of things. First of all is how big does this thing need to be? You look at how much space do I have between runways, because that tells you how wide this thing can be. And then you look at how much space do I have. And then in this case, do I access the terminal from a side? I have the roadways here, they drop me off, then I somehow work my way through, right? And do I do that as a long stick? Do I do that like a big X? Do I then take the train and come out? Some of you may have been through some of these airports. This is Hong Kong. Again, completely walking terminal. Now you have a satellite. Or do you have a terminal, for example, that you get from both sides, like in Atlanta or in Dubai or in Dublin? Now you have the new terminal will be on both sides. You know, you can check in on both sides and go to one of these piers. There's many ways of solving this problem. You can put also something in the middle, like in Munich. Right now we are redoing the land side, meaning on the public side. We're doing all the landside infrastructure right now, which is all the retail shopping. We're doing this bit. Heathrow, which you know is a big mess. It's being changed. They're adding lots of things, taking lots of things out. JFK, Chicago, all kind of in a surrounded configuration. So one of the things that we've been doing is doing a little bit of research on the side, which looks at what are some of the parameters that we need. As I said, one of the things that we have is runway spacing. That means from runway to runway. When I control these in a parametric model that gives me feedback, I can actually look to optimize what is the layout that I need. In this case, I increase the runway spacing, but it tells me in this case now it's so far that the walking distance is too long for people to walk and make their connection. So this, doesn't work. So I can reduce the spacing or change the spacing, the recalculation happens, and then it'll tell me probably that this might work. So now it reduces, perhaps in this case, the spacing. It will tell me it fits. In this case, it's an IATA rule. You should have walking distances less than 600 meters. If I'm above that, it becomes too long for people to go. So I think this is one I had. Okay, so what happens is you end up now with a search system. In this case, you have a body of search that gives you a number of parameters that you need. One of the things you need to know is what you call the contact apron length, which is a distance all around the terminal that tells me where I can park planes all around this thing. It tells me how many gates I will have. This is like where you have the little jet bridges. How can I connect? Mars stands meanings I can park either one big plane or 2 little planes, so I can have maximum flexibility. And in each one of these, you'll see these numbers change. It gives me different layouts and different conditions that I can then optimize or control against other parameters. For example, I might get a more centralized shopping area. Very good. Everybody has to go through shopping. Today, airports have to generate at least 50% of their revenue, not from landing fees, but from retail. So I'm talking about concessions rental, so Gucci and Prada renting spaces, or McDonald's, advertising, food and beverage, dining, all this kind of things. So it suddenly becomes the idea, ironically, that you take something like Westfield, if you've been there, and you park a bunch of gates at it, and that's exactly what people want today, right? So Westfield with gates on it. So again, it has then the downside that you might have to go further to your gate, so you take the little train. So what's the downside there? You have to pay for it. You have to keep it running. If the train breaks down, you're in serious trouble. You need now suddenly 100 buses to bus people over here. So pros and cons, risk assessment. Again, what do I need to do? So I think this is, whoop. This is another little video that showed you, I wonder if I can click on here and go enter. Whoop. Sorry about that. So what this one's showing you is, this is that contact stand length. And what the system is doing in real time, it's a little accelerated here, is by looking at different configurations, it will give me very quickly that output and tell me how many planes I can park. I know roughly per MPPA I need about 100, 120 meters of contact stand length to fit the aircraft I need. So if I have a 45 MPPA aircraft, I need 4,500 meters all the way around. What's the best configuration? All of these will meet it, but maybe the aircraft mix isn't right. Maybe it's too far to walk. Maybe I don't get enough shopping in there. So this is what goes on for quite a long time. So you end up, this is taken from the Navi project, the new airport in Mumbai, that we are the lead consultant for, so we're driving this right now, is looking at a basic taxonomy that the client gave us and said, how can you improve this? So you say, well, do you have an evolution? Do you have a revolution, saying, screw that, I'm going to do something totally different, like having satellites instead? Or do I just try and optimize and see how much I can shoehorn into this thing? So this is, again, like this evolution of possible layouts. And so this is from the project. You're looking at what kind of aircraft can I park? I'm going to have 3 terminals. I'm going to build them in a sequence to offset investment. I'm not going to build one great big giant terminal in one go because I don't need it. Now, do I pinch it more here? If I can pinch it more here, people walk less because they don't have to go all the way around. I can put some bus stands here where they take you with a bus. And you keep on going until we finally came up to this is final optimized layout, which was a selected one, and this is the one that's going to get built. So it goes down a particular path of optimization and testing and consideration before you come out with the actual plan of what this is going to be. So, to conclude, what I'll show you is an actual built project. This is the one we opened last week. This is the Beijing Airport. It's the second airport in Beijing, so if you go to Beijing, right now you end up in the capital airport, but as of last weekend you can now fly here as well. So they had Heathrow, now they're building Gatwick, or they built Gatwick now, but except the Gatwick is bigger than the Heathrow. So this is one of the 2 largest single volume terminal buildings on the planet today. It is 700,000 square meters in the main terminal, including a railway station underneath here, which you'll see is the size of Paddington. Hotels and administrative buildings and car park were almost 1.5 million square meters of construction that we were responsible for designing. And tip to tip, it's 1,450 meters. And the reason being is the calculations of the walking distances you perform from the edge of what you call the main processor building down to the ends. And it has a few interesting features, as you'll see, one of them being the fact that you have this very intuitive progression through light. So people come in here, they follow the light, they have a great big central space that they orientate themselves with, then they follow the light down one of these piers. It becomes very intuitive navigation. Remember, this is about expansion of air travel in China. A lot of people who are going to go to this airport have never flown before, never seen an airport. So the building processes aircraft capacity for 45 million passengers per year. If you add the satellite that there is already in planning now, which goes in this green box that will go out with the train, that'll be 72 million passengers. And 72 million passengers means that all of those passengers will be checked in and reclaim their bags in this building, and some of them will just take the train out. To give you an example, the planned functional capacity of Heathrow is 69 million passengers per year for the entire airport. So this building will process more than all of Heathrow combined, right? So this is a couple of years ago, going up. You can see the railway tunnels underneath here. It's very big. It's the size of, like, it really is Paddington Station. Parking going up, space frame work, cladding going up. I'll show you a few more pictures, obviously, of this. And I want to show a picture of this guy. You know who he is, because Xi Jinping, right, the president? The reason these projects happen over there is because they're a project of national importance. And by that, I don't just mean politically, I mean they really need it. They really need it because the capital airport was functioning, by the time we opened, it was functioning at over 105, 107% operating capacity, so it was basically bursting at the seams. could not be expanded further due to lack of land because of the city growing around it, and also because the airways, the flight paths are full. So cannot put any more planes through that. So they have 3 national capital projects in China. One is the Three Gorges Dam, which I'm sure you're aware of, this big dam on the Yangtze River. The second one is the entire high-speed rail network of the entire country, which is now at 18,000 kilometers, and we can't even build HS1 here. They've built 18,000, I think, in 12 years. And the third one is the Beijing Airport. So very important project for them. And one of the things that's worth noting about this one is that historically, Beijing, if you know Beijing, is a series of concentric boxes, squares, and the innermost square in the innermost sanctum is Tiananmen Square and the Forbidden City. That was traditionally, for hundreds of years, the configuration of the city. And the way you enter, if there's people here of Chinese background, you may know this, you enter through a series of ceremonial gateways, Yongdingmen, Tianmen, Zhenyangmen. They put Chairman Mao's mausoleum on this axis, then the famous Tiananmen, which everybody knows. And then you go inside Duanmen and all the way through the sacred temples, right through the Forbidden City. So it's kind of going more and more to the imperial heart, the sacred heart of China. So if you extend that axis, the imperial axis of China, lo and behold, the airport sits on that axis. And that is very interesting because we said, look, if you think that the work that was done for the Olympics, it was configured to look like a dragon because dragon is a very powerful symbol in China. Then we said, well, our airport is more like a phoenix. And in Chinese cosmology, it's worth pointing out that the phoenix and the dragon, you will always see them together because they bring balance to the universe. So for them, having a phoenix and a dragon means that the city is very well balanced. And so we said, well, this is now the Phoenix Gate of China. So we call it the Fenghuangmen. And it is, frankly, the new gateway by which you enter China. You used to just ride your horse into these gates, and now you fly into Beijing through this gate. So it is more than just an airport. This is another thing I wanted to point out for you, is that all these projects today are being done as what are called multimodal transport hubs, which means that you no longer plan an airport, you no longer plan a railway station, you plan them as an integrated transport system that includes roadways, they build huge highways, a fully integrated high-speed regional and airport express network, including the tube, and then the airport sits on top of it. So some people will be traveling between Tianjin or Beijing, and they might change train in the airport station but never actually make it out of the station. They just use that as an interchange as a railway station. Some people might change planes in the airport from one flight to another, never get out of the airport. Some people might arrive by bus and take the train. Who knows? It's a multimodal transport hub, multiple modes of transport. So we're somewhere over here now. We finished. It was a very long process in which we, I think it was about 40 teams applied to do this project. They selected 7, of which 3 were mainland Chinese teams, and who we knew would then be later be involved in the construction, and then 5 foreign teams, of which 1 was ours. And we had a fairly multidisciplinary team because we were still getting started in this business, so you have to bring in partners who know how to do this. Very long bid stage due to changes in the administration. They moved from the Hu Jintao presidency to the Xi Jinping presidency. That took a long time for them to make design revisions and optimizations before they finally selected a final integrated team, and after that it was go, 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 go really fast all the way through to construction. Our office has had 4 different engagements or 4 different contracts on this project, so it's not usually just one shot. We had the original design competition and so-called optimization contract, which is effectively designing multiple stages of development before they finally select the project. We were, again, the lead consultant for this, and we worked with a range of engineering teams you may well know, including other architects such as Pascal Watson, who do a lot of aviation planning, and then other consultants such as McKinsey, who are strategy consultants to tell you roughly what you need in the building. We then formed, under the client's auspice, a very international process, as you can see, a team with Aéroport de Paris, who's another competitor, and they said, look, your projects are very similar, but we want you to combine the best of both. So we want Zaha's design, but we want some of the planning features coming from ADPI. We then won a completely separate contract, was to plan the interiors and the retail. So this was very much about retail layout analysis of type of retail demographics that you need, footfall, type of shopping mix, layout of shopping and retail that you need in the building to, again, generate as much money as you can. And then finally, we were retained as a design guardianship sub-consultant to the executive teams in China, which is the Beijing Institute of Architecture and Design, China Civil Aviation Construction Company. In China, as a foreigner, you must go in the latter stages of design, you must hand over to the Chinese by law. So you take it to roughly about RIBA stage D, and then you hand over, and then you carry on. Old D, or now probably stage 3. So multimodal transport hub is basically an air terminal. It's a roadway system that accesses us with a series of motorways to the city. It is a railway station, a very large one, and then what's called the airport city, which are all the office buildings adjacent to that, that also provide, on one hand, support, so you have airline offices, hotels, training schools, and so on, but also become an investment zone. So what the government in China has done now is they've taken the new airport, and around that, between the new airport, Beijing and Tianjin, have developed a new special economic zone that allows you now to have tax-free investments and really create a whole new area of business in this. So the airport, in a way, becomes a catalyst for that. So the scope, how you split this down, becomes interesting, where you have one part of the team working on architecture and design and the structure. Together you work on spatial technical planning, how the building really works, how do people move through the building, what do they experience, how do you process them. And then you have technical planning that really looks at the functional characteristics, which means things like occupancy, means things like capacity planning, making sure that the airport really does what it has to do. So this was the original competition model that we did. This is a good image here because the model was literally this big. In fact, there were 2 of them. This is just the terminal. And then there was another model this big, which was the entire airport. So really, really huge model. So, and this is for all the competitors, so this went on for miles. And you can see already in the beginning, in the inception, you have the 6-armed star with the central space, and then guiding people along down to the piers. And this is something that was possible because of the runway spacing that allowed us to have these wide-fingered piers. And also, more importantly, again, it allowed you to walk everywhere without the need of a little train. And to the client, this was really, really important because they did not want to have the headache, which they had in the other airport, of having little trains and doing that. So the way that it works is that the client took the planning scheme, you see the 2 6-armed stars, and combined them, the planning with the architecture, to produce the final scheme. And this is what we developed between Beijing, London, and Paris, and then executed by the local design institute. So this is effectively how the design came together. And a lot of this really was a cultural experience, because you're going there and you don't understand the language, we had the good fortune that we had already built at this point 2, 3 projects in China, in Beijing itself. So we did know the design institutes, we'd worked with them before. The airport, I think, is the 4th project we completed with BIAD. So we had a good working relationship, but the client had other requirements, learning to work with them, sitting them with literally, we were locked in this room for months and months and months before heading back to London and Paris to complete the work. And you really have to learn to work between teams, between companies, at different times of day, night, interfacing with London, interfacing with Paris, interfacing with other consultants around the world, to really, really meet the deadlines to design something of this complexity, and also ensure and convince people that what you're designing and you're proposing really works. So what is special about this building? Well, it has a couple of interesting things. One, as you will see, is that it has some special processing features. The other one is that it has to be, as I mentioned, intuitive. It has to be pleasant to use. It has to be flexible, resilient. This is going to change over the lifespan of 50, 70 years of this terminal. The interiors will change. Things have to be move-aboutable, if you like. And so what we had was effectively a solution where we said everybody in this building should experience that same central space. So if you're flying domestically from these piers, or you're flying internationally from the South Pier, everybody should be able to come through a central space. And in the early sketches that we worked through, that was very much recorded, the fact that we wanted to have everybody having the opportunity through a series of layered bridges and canyons, that everybody could go through the same space, and also, more importantly, not just departing passengers, but arriving passengers too. Remember, it's the first place you're going to see when you arrive, and as you know from many airports, you arrive and when you depart, you have this great big hall with huge, beautiful columns. When you arrive, you're in some kind of tunnel, and the baggage reclaim is really low, and it looks like in here, and that's the first thing you see of it where you arrive, and that's not good. So we wanted to create a space that really worked for everyone, and that became this project here. So to explain to you how this is put together, you think covered obviously by some nice roof, but you have typically what you call a full service departure level. That means where you go at Heathrow and you have these islands or rows of check-in, and there'll be a check-in person who will take your bag. You'll say, can I have an upgrade, please? Is the business full? You know, you do that. And you try and get a nice seat by the window, right? And that's your full service departure, means proper check-in. That takes you to an international departure level. And then you have also a domestic level. And in China, arrivals and departures is mixed. A bit like in the United States, you do it on one level. You don't have separate arrivals, departure levels. Then you have the same thing on the same level for international arrivals, and you have an international arrivals, and you go out to the street. This is typically how an airport works, right? You have a drop-off level, and you have a pickup level, right? You guys all know this from your airports. What's new about this one, ta-da, is two things. One is you have the railway that is right, not next to it, but right underneath the terminal, and it accesses all level. This is this integration of multimodal transport hub that I mentioned, which you'll see in the construction pictures. And even more importantly, the Chinese government recognized that in China now there's more mobile smartphones per capita than anywhere in the world. Everybody does everything with WeChat, paying things, buying things. So they say we have an entrepreneurial class emerging. They're being basically weekly high-frequency commuters, and they commute between Beijing and Guangzhou and Shanghai. They just come with their little wheelie carry-on bag. They don't want to wait in line and get checked in. They just walk through, a bit like when you're on the tube. They just tap in with their mobiles with a QR code, beep, and they just walk straight through. Facial recognition scan to check your ID. Really quick through self-processing, high-frequency domestic departure. And they were so committed to this that they say, we're actually going to build a completely separate floor slab to house this with a completely separate drop-off. This first kind of this anywhere in the world. Very interesting to see. And again, all tied together with this beautiful atrium that everybody can experience as a central space in the building. So this is effectively the base configuration. You like this? It's nice, no?
Sorry.
No, it's okay. I'm just talking to her more. So again, the way that you do this then is you're looking at how can I maintain flexibility and resilience? So you're doing this with long span. This is probably the longest spans in the inside of a building in the world today. We're spanning up to 120 meters between 6 mega columns in the center. And that means that everything else inside, shopping pods, check-in area, we can move all that around over the next 50 years. Tear stuff out, build new stuff. It doesn't change the envelope of the building. This is hugely, hugely important to maintain operations. So the way we knew how they could do that, as you can see, S-frame, space frame, is we knew that the Chinese had developed a very, very efficient way of building space frame long span systems. Without this understanding of the local construction industry that you're going to work in, you will not be able to design something like this. So the idea that the architect designs something and then somebody's going to build it no longer applies. You must from day one understand what are the parameters that will allow you to create the design options that you need to build this project. And you see that in the cutaway here, right? You see these big columns. These are columns underneath in the lower levels, but in the big free span area, there's no columns at all. It's completely free. Everything can move around. Everything can be reconfigured. There's the big railway station underneath in the north arm, the sixth arm, and the aircraft parked here. So one of the things that we had was this idea of intuitive wayfinding, of finding your way through light. This is something that the office in Zaha likes to do. If you think of the Maxi Museum in Rome, we have these avenues of light in the ceiling. Same thing here. And you know that you're going to follow this down. So in the construction, you see, again, this is something that we maintain. You see these huge column-free spaces, and then these are little blocks that I can move around as need be. You can see the size of people here. You can see also the space frame. I'll talk a little bit about these cannonball space frames, how they work. Everything was developed on the digital platform. Suffice to say that this is done very much through generative structural design. So this is not just a pretty shape that somebody drew. This is actually worked on with Wolf Mangelsdorf and Rob May at Bureau Happold. Bureau Happold being the same team that did the form finding for the dome, for the glass systems at the British Museum. The idea, this is a form-found optimized structure that allows us to offload the loads onto a minimum amount of columns, right? The Chinese did a fantastic job because they took all the information in the downstream where they had to be in the lead and took this through BIM right down to the level of rebar modeled in the computer. So it's a huge task, but it's the only way to be able to make sure that everything fits together. Think of that Boeing image I showed you of the 777 3D model, right? Everything has to snap together on the job site. No time for reworking, no flexibility for abortive work. Everything has to come together. Every single node is tested and modeled and put together in the 3D software to make sure that it works. Very fast timeline. We started on Boxing Day on site of 2014. By the end of 2017, the building was enclosed. And by that, I mean weather enclosed. Then interior fit out, which we finished in the middle of this year. The last 2 quarters, we were conducting ORAT, which is basically what means operational readiness and transfer, which means you're testing the building, as you will see, to make sure that it works on day 1. The baggage goes where it needs to go. People get to where they need to go. And then we just began service. Just in the central part of the building, not the piers, just the central processor, just gives you a little bit of idea of this. Some 3 million cubic meters of earth were moved. Some 600,000 cubic meters of concrete were poured. In the entire building, over 1.5 million cubic meters of concrete were used. We had something like 40,000 workers on site at peak times with 80 cranes, 80 of those big cranes, to produce 82 contact stands being the ones with the arms that you dock the aircraft at, with 4,000 car parks, as I said, over 1 million square meters of construction when you put everything together. So this was Boxing Day in 2014. So this is taken with a drone, and you can see they're putting in the first stone. I have a picture of these old ladies putting in the stone, but I didn't have it in the slide deck, so I'm sorry. But I can send it to you if you want. All the earthworks were modeled in 3D. So this is looking at, to excavate the site, what is the total volume, and then you multiply that by the number of trucks and how much volume they can take, and it'll take you, I don't know, they'll have maybe I think 2,000 trucks on site. Will take them, I don't know, 5 months to dig the hole just for the railway station box, into which we then poured and pushed 6,000 piles in the core area of the station. So this is just the underground station box. It's like if you take Paddington and you squish it down to like -14, this is what you get. This is before you've designed any terminal at all. Then you start coming up. I've taken out some of the slides here just in the interest of time. This is now grade beams. Very, very huge amount of management on site because these are all migrant workers. So you have the foreman checking that everything's coming together. So these are the grade beams under the station. Once the concrete is complete, you can see these are cut and fill tunnels of all the railway lines and all the people movers to the satellite. They're all safeguarded, all built. So there's a huge station, you can see the box here, underneath that multimodal transport hub. And you can see then, out of that now, this roof starting to take shape. So the roof, as I said, they're basically 4 identical parts, and then the central part are 6 identical parts, mega columns, spanning in the middle. In this area here, it's 90 meters. Tip to tip, it's over 100 on these mega columns, given out to different contractors. This meaning chu, which means area, so area C4, C4 chu. And this, as you can see, it's a very simple tripod. 1, 2, 3 points of support, and spanned by long span space frame structures support the entire roof. Well over 100 meters in each direction. So these are fabricated steel mega columns that have this branching. They're installed on site. And you can see here then the space frame being welded together. And then these are so-called strand jacks. And once you have that together, the strand jacks together push the whole thing up, and you connect it to the main tower. And then you have then the other touchdown points. I think they're off screen here. And then you get something like that. So this is the central atrium over here. And this is now these big light domes. So the way that they do these space frames, if you know space frame technology like Miro, M-E-R-O, if you look them up, they're normally these prefabricated spheres or octagons with drilled holes, and you screw them together like an erector set. Way too slow, and most importantly, they cannot span that far. They're just not strong enough. So what the Chinese have been developing over the last 20, 25 years is this idea of using these giant spheres. I mean, they're huge. They're like this, right? You can see how big they are. And what they do is they use lasers to align points on them, which they then weld either by hand or robotically, and they very quickly put together the space frame way faster than you could with a system. Having modeled and lasered out each point of the weld. Very, very fast, extremely efficient. So here you see the strand jacks lifting these things up. Sorry about the quality, it's not very good. But you get the idea what's going on. You build it, you lift it, you fix it. Done. Right? Again, you see the scale of the people here. So where we are right now is looking into the main central area. This is an international upper level up here. These are now the beginnings of these shopping pods already going in. And then this you go down to the bus gates to take you when you need to take a bus to the airplane. So this is now the roof. This is now spanning this 90 meters and over 100 over here. These are these great, huge light domes and these 6 mega columns that are supporting that entire thing. You can see people here. They look like ants, little dots. And one of the things that has to be said is, of course, the level of work that you have in China. You have the manpower, you have the human component that allows you to do this very quickly. In this case, we're laying a standing seam deck on top of these calipers here. To have this many people doing it this quickly allows you then very quickly to span long distance, and you get this kind of eerie landscape. We were giving a presentation together with a friend of mine from Grimshaw's yesterday at Heathrow. I said, this looks like the Eden Project in the mist, you know. It's got this kind of weird landscape equality, and you don't really realize that until this thing really comes together. So on top of this, then you get a lot of decorative panels, which are bright gold, dark gold, and then these are these drainage channels all around. Here, this is on top of the dome. The decorative panels are missing, but these are these main light wells. I have a whole other deck that explains how the lighting system works, but I'll leave that out. But this is what you start getting, really that effect that you looked at for so long. And when you start going on site, you really understand the scale of this thing and start seeing kind of the fruits of your label. Here we're looking due south along the main axis to the international pier. These are these domestic piers. Follow the light. And again, you know, there's some kind of heroism to that. People really welding, climbing, doing some very crazy things to put this building together. And it reminds you that in the end, it is kind of a giant human exercise to put something like this together. So this is like, you know, space age sunset image, people working 24 hours a day. So then the building finally emerges a little bit from the mist. And I'll show you a little, I think we have sound here, right? I'm going to show you this. Enjoy that. Don't have to listen to me talk all the time. So just to conclude, I mean, when you talk about operational readiness and testing, this is what it is thousands of bags that are being put through the system, and then they have thousands and thousands of people. So they get all the workers, all their families, their kids, everyone to come and pretend to be a passenger, and they give them fake boarding passes and see how long it takes them to queue up, and does the machinery work and not break down. And it's actually quite interesting. So we participated in that a little bit. You can see after 8 years of work, we're very tired. This is Satoshi, he runs our Beijing office, Ed runs our New York office, and you know, we're kind of at the end of our rope after all this. And so last week, they said the Central Committee came of the People's Republic just before the 70th anniversary and opened the airport, and the big man showed up again and declared it open. And the next day they had the first flight, which conveniently was an A380, China Southern, flying out of the new airport. So, thank you. That's it. Yeah, no problem. Anybody have any? Yes, ma'am. Sorry, we need to hear the question, guys, otherwise I won't do it justice. The exterior cladding. So the exterior cladding, as you saw, is a standing seam system. This is something that we proposed early on because standing seam, which is like, you guys can look up, for example, CalZip, right, is a good commercial product. The technology, it used to be just a parallel straight thing, but now there's technology that allows it to twist a little bit, and also you have the ability to perform, this goes back to the Galaxy project, you can perform what's called elastic deformation, which is different than a plastic deformation. So you got a certain level of flex, and you have laser machines that can cut the width of these strips now to actually get these fluid surfaces. Then on top of that, we placed rain screen panels, which are these decorative dark gold panels that you see. This is something that the client really wanted because it's an important color in China. And they let the rain pass, and that's caught by the cladding below. Okay? Yes, sir?
What were the effective ways to calculate the accurate amount of bill of quantities in this project?
So, this project, the final bill of quantities, is handled in China, and they will never release to you what exactly that was. You read a lot of interesting numbers in the press. They're all wrong, I can tell you that. Actually, sometimes because people either have a zero too many, or they write they write $ instead of Chinese renminbi, and suddenly, you know. But the way we're doing it on other projects, including the airport in Mumbai, is we work very closely with the BIM model. And the BIM model gives you a very, very accurate bill of quantities that you work with your cost consultant to apply particular rates to then have a very accurate construction model. So the BIM model, so we produce an early stage BIM model, which we handed over to the Chinese team. That's the only way they were able to get the geometry right. We had a separate BIM model that documented the interiors. We handed that over. The final version of that was handled by them. In the case of Navi Mumbai, through the first 2-3 stages of design, we're controlling that. We're just waiting for a contractor to come on board, and then they will control that too. But it's the model, the one that really contains the information. Sir? Good question. The way that I would answer that question is through this image, or maybe that one. It's about will. Where there's a will, there's a way. So if you look at the high-speed railway system in China, they started on this, I think about 15 years ago. They're at 16,000, 17,000 kilometers of high-speed rail. That's more high-speed rail than the rest of the planet combined, right? Here we're still umming and ahhing and now canceling, postponing HS2. It took them 18 years to do HS1, which is a pathetic 100 miles to the, you know, because of NIMBYism, because of many other issues. It's not that technology is there. In fact, some of the best engineering, planning, architectural consultants in the world are in London. Think of Arup, Mott MacDonald, many architects, you know, they're all here. But we have to go abroad to do these projects because here, like I said, I've got mates working at Heathrow and they're like tearing their hair out because they just can't get anywhere. Or it takes them a very long time. So the answer is yes, the speed of construction is possible because the technology is there to enable that. The issue is really what are all the different processes you have to get through for the planning, environmental impact. What they do in China is they fast track those. For example, we're working on a new project in China right now, another big terminal. And the way, for example, that you solve fire code in China is here you have to file and follow all the fire codes from the beginning. There you do too as well to an extent, but what they do is then they convene what are called a state expert panel, which will review the project from a fire engineering standpoint. And they will basically sign off a basic functionality of the fire code, or rather the fire performance of the building at the further design stage. And that means you expedite the approvals process, right? And this is something that you need as well. So in answer to your question, yes, it is possible. They opened a new terminal, I think it's even a bit bigger than this one, in Istanbul recently. That was a Grimshaw project. There's a big new project that will happen hopefully soon in Eastern Europe, similar size. These things are possible, of course. The issue is, one is the will, the other one is expediting the process, and the third one, which I won't exclude, is the financing. So the financing here is done by the Chinese federal government themselves through what's called the national, I left that slide out in the interest of time, but there's a team there called the National Development Reform Commission, which is essentially the federal purse strings of China, who, through various forms of income, taxation, and so on, they're able to channel money to strategic capital projects. Because again, there's a decision to grow the country, we have to have the communications and movement infrastructure that's required. Without those things, we can have all these great ideas, great engineering team, great consultants. You don't have the vehicle to do it. Sir?
What was your greatest sustainability challenge in the project?
In general, on this project or in general? Let me put it this way. There's two sustainability issues, right? One is the building itself, and one is the performance of the building. So one of the things that we did, you may have noticed early on, is we took the building, rotated it 30 degrees, so 6-armed star, but 30 degrees, so one pier is pointing up, one pointing south. What that allows you to do is reduce the runway spacing by 13%. This in terms reduces taxiing time, the time that it takes the aircraft to get to a gate, which you're burning less fuel. So that's an operational sustainability that you're improving just by reshaping the building, reducing the amount of taxiing time. Another one would be, for example, the elimination of the people mover. By having people just walk or using travelators but not having the train, the energy that you require to operate that automated people mover, again, is removed. So those are operational sustainability factors that you can mitigate just through design. Yes, ma'am. Sorry, I can't hear you. I'm old. Istanbul, the new Istanbul airport. So I was just there maybe 3 weeks ago. I went through it. And one time my connecting gates, because I was connecting to somewhere in Asia, I can't remember where, they were 2 gates apart, so I didn't see. On the way back, actually, they were quite a bit apart. And what's interesting, the airport there is, it's a little bit bigger than this one, and mainly to do with the walking distance. And what was really interesting, and my colleague here is going to appreciate that, you have a factor, for example, that you have in aviation planning that's called the call to gate time, which means that when you're in an airport, you'll know this from Heathrow, you go and it says wait for gate, or please wait, right? You know that when you go to Heathrow it tells you wait? Why do they do that? Any guess? No, so you don't go to the gate and? Shop, exactly. So you can part companies with your money. They want to keep you in the shopping area, walk around, oh, Gucci, oh, Rolex, right? That's what they want you to do. They want you to stay in that mall and not go to the gate. However, if you tell people too late, oh, my flight's going up, then you're late and you panic. So you have to have a meaningful call to gate time, which is when they finally announce when do you need, please go to gate or boarding soon. Or to Heathrow, they go to gate, boarding, closing, in 1 minute, and you're like dying, right? So in Istanbul, the call to gate time was 2 hours. That's how big it is. So I was in the lounge, my flight to Heathrow, I came in overnight, and I was in the lounge at 5:45, I remember. with a colleague, and the flight was at 7:45 to Heathrow, and at 5:45 it comes up, go to gate. And I'm like, is that the right flight? That must be the early flight. No, it was my flight. And in fact, the gate wasn't that far. The reason they had that is because it was a big plane, a 777-300, which is the big one. And in Istanbul, they have to have extra security checks because you have people coming from, less secure countries. They might be coming from Egypt or Iraq and connecting. So the secondary screening that you do at the gate to screen 350 people takes a long time. So that was the reason. So, but other than that, it's beautiful. And it's interesting how it differs from this one, because again, we were at Heathrow and Andy Thomas from Grimshaw was there, and we both showed the projects. In that one, that government wanted to capture features of Istanbul, which you have these domes and this lights effect. Here, they wanted to capture this Phoenix feeling and these flowing lines. That was something that so different places have now different identities. Like when you go to Istanbul New Airport, you'll definitely know that you're there. You go to Beijing Dashing, you'll definitely know that you're there. In fact, worth pointing out, shameless plug, from end of this month, BA actually shifting their operations from the old airport to the new airport. So if you go to Beijing from, I think, the 26th of October this month, you will be actually flying here. No, I just have people have questions.
A couple of things I want to say. Firstly, the feng shui line through Beijing,
Yep.
we talked about, which runs from the Olympic Stadium with Bird's Nest through Mao Zedong's mausoleum through the Forbidden City. Mao Zedong built the mausoleum across the feng shui line, which is part of the Cultural Revolution, because he said, I don't believe in any of this. And I think it's important to remember this. He cut it. He cut that belief system.
Yeah.
They are continuing that belief system by building on the same line, which is kind of strange. I know lots of people, the questions that I know these guys want to ask, but really wouldn't ask you is, what do you think, how would Zaha entertain what you've done there, for one thing, and just also kind of an addition to that is, I can't remember. Anyway,
I can answer that first if you want. And I know you have a question back there. So I can say this. So Zaha, as you know, passed in 2016, it's about the same time, it looks like Brexit. Anyway, she passed a good 3+ years ago. And so by the time she passed, this project was well in construction. So she was intimately involved in this job. And when we actually did the original competition submission, she came out to Beijing. She actually spent a long time during the competition process defining what this language should be and understanding also what a lot of the functional parameters were, which was quite amazing because she's a busy lady and came from a different line of thought that was perhaps more aesthetic. But here, because she herself spent so much time in airports, so much time traveling, she had a relationship with this project immediately because she's like, I'm in the airport every other week. I know what the issues are as a user. So she was very, very interested in that. So I think she'd be very happy because the final design she was very much part of. And like I said, we started construction Boxing Day 2014. She died about 15, 18 months after that. So she was well informed.
It's been an enormous privilege to have you here so quickly after the completion, so thank you so much.
That's a good coincidence. Yeah, if you have any further questions, you can ask me or email me. You got to go. Yeah. How was it? Was it okay? Was it entertaining?
You always make entertaining ones. It's very good. They were better than one I saw last time. When was last time? Last time it was at far away.
In Bartlett. Yeah, it was the